Hello everyone, I've been working on my video game for a long time and I thought I should start to get to finishing it up. And so I made this list for myself. As you can see, there's a bunch of things I need to do. And for the past week I've been working on one step of this thing right here. And I was finally able to accomplish one step of the enemy AI, which is just the walking part, and I feel very accomplished. So I want to share with everyone how I did it. So in my video game I'm using the tile maps, where there's a procedurally randomly generated map, and then there's enemies and there's a player. And what I wanted was for the enemy to be able to follow the player at any kind of map using the A-star pathfinding algorithm, but it would also know to not walk into walls and whatnot. So I use two main guides, I would say, to learn how should I approach this, and I will show them on the screen. But I mean, they're great, they're super in detail, they helped a lot. But the thing is, most of them, they start with the game, turn the game into a array, and then I use that to get the directions. But the thing is, I'm already using tile maps for my video game, so I thought I should modify it for my own benefit. And I was finally able to get it to work. So let me show you here. If you run the game, in here, the red is the unwalkable parts, and the white is the walkable parts. You see the enemy here, and this is the player, and this is the way that it needs to move on. So for example, if I go this way, the path constantly updates wherever I go, as you can see, which is quite neat. And also for debugging purposes, I drew this green line which points where should the next step be for the enemy. Right now it's that way. For example, if I move up, it's going to update to look up. Right, pretty neat. Right now the enemy is not walking because the speed is 0, but if I set the max speed at 1, you'll see that he starts walking. He's going to speed up slowly, and once you reach the max speed, you can see he's constantly updating, slowly walking up. And if I stop walking, he's going to walk up to me and reach me and then stop. But if I start moving again, he's going to constantly update the path and keep following me. And I can, if I want to create a different map, we can make a bigger map with a different seed, but it's gonna still work. Oh, is my enemy in the wall? God damn it. Okay, I need to position him a little higher. So yeah, right now we're in a different map. Again, I need to give him some speed, but once I do that, he again starts to chase me. This looks quite similar, but yeah, basically in any kind of map this would work, and he's gonna completely chase me. I think right now the problem is they get stuck on corners, which I'll need to fix later, but it's doable. The main thing works. And I also want to show how I did this. So basically, okay, let's just go to the single version. Yeah, here. So first of all, we have so these, I got a lot of my inspiration from the videos I initially showed, but first of all, I defined a node. So a node has two things. It has a boolean, which is is it walkable or not? For example, if it's a wall, it's 0, it's false, or not, it's true, it's walkable. And this was a coordinate, where it is, okay? And those is the cost because of the A-star pathfinding algorithm. So the costs are, I'll try to show an image on the screen, but the costs are basically what's the cost of going? I believe that's the H cost. One sec, let me look at it quickly. Yes, H cost is the distance you need to walk, and in this case I have defined it as if I have a coordinate here, another one here, and another one here, going straight costs 1, and this is also 1. So therefore going diagonal should cost me square root of 2 from Pythagorean theorem. But in order to not deal with fractions, I just multiplied everything by 10. So going straight costs 10 and going diagonal costs 14, which is square root of 2 is about 1.1 whatever, right? So that's how it works. So it first, and this is another function in the node, which is to calculate the F cost. So the G cost is how far away from the target, and the F cost is just adding those two things together. Okay, now we go to the grid. In the grid, we get the world size, which the procedural generation script, which creates the map, gives the sizes to the grid, and it creates a node grid from those sizes. It gets the upper bound of the map for the size of the X and the Y. It creates the grid, and then for each element in the array, it's gonna first check is it walkable. If the map's value is 1, which means it's a wall, it's not walkable. Otherwise, it's gonna be true, it's walkable. In the future, if I add different things, say I add a water structure, which is gonna be 2 in the wall, I can just say 1 and 2 it should be unwalkable. So it's quite easy to update from there. And also gets the coordinate, which is very easy because it's just the coordinate of the array. And then it creates it adds the new node by using this walkable boolean and the coordinate. And there's another function to get the neighbors, which is going to basically just get the nodes around it, which we're going to use later. You're going to understand that it returns the neighbors. This is a function I use to get the coordinate of anything on the map. I just literally get their transform because both the maps are created from the 0, 0 position. So if something is at 10 to 10, their position in the grid is also 10 to 10. I just round it up to the integer. And then this thing gets the coordinate and turns it into a node. And this is also going to be used. And finally, this is the part where it draws the squares. It's basically going to draw a huge... it's going to draw a cube. And if it's walkable, if it's not walkable, it's going to color it red. If it's walkable, it's going to color it white. And then if the path is included in that node, which is going to be calculated by the path binding, it's going to color it black. That's why the path is shown in black. And so we got that. And then the path finding finally. In here, we get the seeker and the target. In this case, the target is the player, seeker is the enemy. You can set them to anything you want from the editor. We first get the grid component because they're both stored in the same, under the same game object. And then we need to find the path. We have a find path function which is in the up there, so it's called at every frame. So I first get their coordinates, then I turn them into nodes, the functions I showed earlier on my grid, these two here. Once I do that, so I basically go through the A* pathfinding algorithm, like how it works, right? Like there's an open set, there's a closed set. Open set is the nodes that you need to look at. Closed set is the nodes that you have looked at. So like in the beginning, the current node you're at, you're gonna look at it and you're gonna remove that node from the open set and add it to the closed set. And you're gonna basically repeat it as long as there's nodes in the open set till you go. And it ends in two situations. Either you need to run out of things in the open set, and if you still don't have a path, there's no path. Or if the node you're currently looking at is the target node, you're like, aha, I got the path. So you just gotta retrace path. It's another function. Or in here, we're getting the neighbors because you need to look at the neighbors, you need to see if they're walkable or not walkable, what's the cost to calculate all that for the A* algorithm. And the retrace path is once you have the start node and the final node, you've got to trace the path. So you start from the final node and you go back to the first node. While it is not, you edit and then you go to its parent, so you go like that. And then you reverse the path, bada bing bada boom, and then you have the path that you go from the beginning to the end. And this is the get distance one. So like I said, this is basically saying that if they are perpendicular to each other, it's going to cost 10. If they are diagonal, it's going to cost 14. Or if it's something in between, it's going to cost something in between. But I don't think that's even possible in my situation because I'm using the grids. Okay, so that's how it works. I think you can look more into how the A* algorithm works, but basically I just used the guide that I found. But personally, that guide was not using tile maps like I said, and I used one, and I know a lot of people use them because they're quite neat. So I thought this was useful. If you're also using tile maps, you can basically use this to implement it yourself. And so yeah, in the editor we add the seeker, add the target. Oh, also let me show you that I don't put those myself. If you look at first of all, in the enemy AI, in here the enemy AI gets these components from the A* game object, and it sets the target of the pathfinding itself, because it just looks, if there's no target, it says get target, and get target just finds the game object with the player, this tag player, so it knows the target now and just adds it there, and it will know. And then it's gonna do that, and then also to create the grid, the procedural generator which makes the map, it gets the mygrid again, the mygrid component, and then it creates the grid using map, and then it consumes map, which is the array of integers here, and then it uses that map to first of all get the sizes and also to see if it's walkable or not using 1 or 0. So it's quite neat that way. And let me see if that's all. Yeah, I think I covered the whole thing. I know I went through it quite fast. I just wanted to show it to be able to help others if they're in the same boat. But also, if you have any questions, obviously all situations are different than each other. Feel free to leave a comment, and I'll be able to help. And thanks for watching.